I'm Nikita, and I'm a PhD student at Meta and Oxford, where I work on reconstruction and video motion estimation. And today I would like to share with you some lessons learned from working on CoTracker and CoTracker3. So here we work on the problem of pixel-level motion estimation. And the reason why we work on that is because we wanted to solve reconstruction, dynamic reconstruction, and we thought it would be useful for this problem. There was two approaches to motion estimation when we started working on CoTracker. The first one is single point tracking. It's when you track individual points for long term. Examples of such approaches are PAPES and TopNet that reintroduced this task. Then there is also optical flow when you estimate correspondences between a pair of frames, and these are dense correspondences. And draft here is still a go-to solution for optical flow. So let's look at predictions of a single point tracker. We can see that its predictions are not very globally consistent, and that's a problem of such trackers, so that points just drift relatively to each other. Then, if we look at the predictions of an optical flow method, such as raft, we can see that predictions are globally consistent, but on the other hand, it cannot deal well with occlusions, so that points just get accumulated on the front of the car. And those are background points, so that it should not be happening. Okay, so we have single point tracking, we have optical flow, and in CoTracker, we would like to be somewhere in between. So that we want to track points for long term, but we also want to do dense tracking, as dense as possible. In pixel level motion estimation, there is a bunch of challenges, such as, for example, occlusions. And optical flow methods just fail here, as well as other single point trackers. Then there is also long-term tracking. The problem here is that changes in appearance from the first frame of the video actually affect tracking, and it's just hard to track such points, such objects. There is also dense tracking, which is mostly just an engineering challenge. It's just hard to make it work. And in CoTracker, we're trying to address all of these challenges with the architecture and the way we train it. For example, occlusions, we try to solve them with joint tracking by just like tracking points together. For long-term tracking, we propose a new way to train such models, and I will talk about it later. For dense tracking, we make our attention more efficient by using proxy tokens. What does tracking with CoTracker look like? We take an input video, so that's just a bunch of frames, as well as starting locations of the points that we want to track. In this case, we have frames number 1, 2, and 4. Then we process the video in chunks so that we take the first, in this case, 4 frames as input to the model, and we estimate tracks only for the first 4 frames for now. And we only estimate tracks into the future. Then we also apply joint attention between points, so that in the first frame, for example, there is only one point. There is no joint attention. But then in the second, third, and fourth frame, there is more and more points, so that we can account for their dependencies. Then we take our predictions from the previous window and initialize our current predictions with the previous window predictions for the frames number 3 and 4. And then we just do the same thing. We apply joint attention and account for the correlations between different points in the same frame. And then again, we just take the predictions from the window number 2 and pass them as input to the window number 3. And we just do it again and again until we reach the end of the video. And the way we train this model is we just take the predictions for all the sliding windows and compute the ground truth between these predictions and compute the loss between the ground truth and between these predictions. And this is what we call unrolled training, because we compute the loss and we backpropagate for all the sliding windows at the same time. While in PAPES, for example, they only do it for one sliding window. And in our case, the model kind of learns to propagate predictions into the future windows. The model is trained entirely on a synthetic dataset, in this case on Kubrick. it contains 10,024 frame sequences with physics simulation, shadows, and occlusions. And yeah, that's it. We just train it on synthetic data. Okay, and it actually works so that we solve global consistency. There is no drift between points, and the model can also handle occlusions quite well, so that background points don't get stuck on the front of the car. This model can also predict quite well, tracks quite well do dense tracking quite well, so that it can track up to 270 by 270 points. Here we just sample points in the first frame of the video and we track them until the end. And this is the first CoTracker. When we were planning to release it, this paper came out. This is a very good single point tracker from DeepMind called Tapir. And as it turned out, this model was actually initially better than CoTracker on these two benchmarks. And this was quite bad for CoTracker because the whole idea of the paper was to do joint tracking and improve over single point tracking. So we decided to study this paper, and it turned out that they actually had higher feature resolutions. So we just took the same feature resolution and retrained CoTracker, and then we ended up here. So it was actually better than Tapir with the same feature resolution. And I guess the lesson here is that it's still important to pay attention to the hyperparameters. Yep. Okay, now we have our point tracking model, CoTracker. We know that tracking objects is useful, segmentation is useful for some applications, but why do we actually need to track points? One obvious application of point tracking is visual effects, because visual effects artists literally need to track points in their work. That's expected for us. But then there was a bunch of unexpected applications as well, such as robotics, for example. There is at least 20 papers in robotics that apply CoTracker for imitation learning. I'm here showing one of them, but also citing 4 papers like that. The way they do it, the way they apply CoTracker for imitation learning is the following. They collect a data set of videos with different actions, and then they estimate motion on these videos with CoTracker by just estimating tracks on a grid of points. Then they train another model with these annotations so that they try to predict the future, like what's going to happen in the future in terms of the motion. They just take the beginning of each video as well as the corresponding tracks and predict the future tracks. Then they train a policy on top of that takes future tracks as input, and it just works better. It's much more data efficient than just training policy from scratch. Some companies also use CoTracker for better temporal consistency. For example, here, instead of detecting or segmenting each object in every frame, they just do it once and then keep tracking these objects with CoTracker. Another surprising application is bio and medical domains. For example, here on the left, researchers are tracking an echo scan of the heart, basically, of the heart muscles. And on the right, it's some kind of protein condensates inside human cells. I'm not really sure what it is, but apparently it's helpful. And I think what is surprising here is that the model still works even though it's not trained on anything like this. It's trained only on this synthetic Kubrick data set. And yeah, it can generalize quite well. There's also tracking of animals for research purposes. And one, I think, super interesting application is controlled video generation, because it's really hard to explain what you want to generate with just text. Sometimes it's just much easier to show it to the network. That's a DeepMind paper that trained a diffusion model to generate video given motion. You can control the video that you generate with In this case, they use Bootstrap here, I think, but there is also a bunch of papers that use CoTracker. I think around 10 or so. There is also a way to do fine-grained control. For example, control the eye of an animal, or even control the camera in an image like here. Here they first estimate point clouds with monocular depth, and then they use motion prompts to control the camera in the way they want to control it. Yeah, I think it's quite cool. Okay, so there was one application of point tracking that was expected, which is visual effects. But then it turned out that there is a bunch of applications, like really unexpected applications, such as robotics, bio, and video generation. And I think the lesson here is that it's really important to make the model that you release easily usable so that everybody can just easily try it and use it in their applications for their tasks. Some of the things that I think we have done are releasing a Hugging Face Spaces demo and a Google Colab demo. Then implementing an easy to use, I think it's easy to use model API, as well as a Torch Hub with a one-liner to really easily try the model. And I think for releasing papers, it's also important to collaborate with AK on Twitter, on X for the release. He really likes nice Hugging Face demos. Then you can also just see how people use the model and learn from that and incorporate their feedback into your work. Okay, let's now discuss the scientific method. I think in deep learning research, actually not everyone is following this method, and I think it's really important because it allows us to really iterate faster. So that's why I think we should discuss it here. The scientific method is the following. We always start with the prevailing theory, with an existing theory. Then we identify its limitations, and we try to formulate ideas, the hypothesis to address these limitations, which we after evaluate critically and test by experiment. And finally, we just adopt the best hypothesis as the new prevailing theory and go to the first step and iterate all over again. So why is it important here? What does it have to do with CoTracker? In CoTracker3, for example, we did around 200 different experiments, and it would be impossible to keep all of these results in memory. So we had to write them all down somewhere. And another thing that we have done here is we had such a table, which is like, that's a template of the table that we had for the work on CoTracker3. We would write down the experiment name, the hypothesis we're testing right now, the results of the experiment, so numbers and some benchmarks, and the conclusion, like whether it actually worked or it didn't. And this was really helpful. So this was the first time I've done something like that, and I think it's really useful for doing research. Okay, let's go back to CoTracker. We started in CoTracker3, we started with the prevailing theory, which is like CoTracker, existing solution. Then we tried to identify its limitations. One of them was it still could not deal very well with long occlusions, like 2 lengths of its sliding window size, for example, or more. Another thing was that the architecture was cumbersome, and there was still a gap between synthetic and real data that we wanted to address in this work. So let's start with long occlusions. We can see here that the tracks just go completely off at some point as soon as they become occluded, which is a problem of CoTracker. So we decided to remove the sliding window completely and try to process the entire video at once so that the model just has access to all the frames at the same time so that it can see what's happening in the past and in the future, which is, of course, not very applicable to online tracking, to real-time tracking, but it's still useful for applications like video generation, for example. So we did that. So that's an offline model, and it actually worked pretty well. We tested it on a bunch of videos, computed some numbers, and we can see that it actually works for long occlusions now. Then for the architecture, the idea was to redesign the whole thing from scratch. We also added vertical relations, which proved to be useful in the local track paper, and we removed the global matching state, which was not very helpful. So yeah, let's discuss the architecture now. It's similar to the original CoTracker, but it's much simpler. Again, we just take a video as input as well as the query points. These are the points that we want to track. Then we just initialize our tracks with the query points for all the frames of the video. We also have confidence for each track in this model and visibility for each track and each frame. We initialize those with just zeros. Then we compute convolutional features for every single frame. These are our feature maps. So we have these feature maps for every frame, and then we sample these feature maps around the query points and compute the correlations between the query point, the neighborhood of the query point, and the neighborhood of this point in all the other frames, so that the model can find the query point in the other frames of the video. Then we just pass these correlations as well as tracks, confidence, and visibility to the transformer, which iteratively updates predictions by estimating deltas to them. Then we just iteratively update the tracks, confidence, and visibility m times, and take the final predictions, and these are our predicted tracks. We compute the sigmoid of the confidence and visibility, and we just keep the tracks as they are. Okay, that's the architecture. We also have our synthetic data thing. The whole idea here was to try to leverage real data and pseudo-label and compute annotations by pseudo-labeling diverse synthetic trained teacher models. The initial idea was to take a model trained only on synthetic data, like CoTracker, then pseudo-label real videos with this model, and filter out bad tracks to keep only good tracks and train on them. So yeah, then fine-tune the same model on pseudo-labeled videos, pseudo-labeled by the model itself. And as a sanity check, we decided to just not to filter out bad tracks and just train the synthetic trained model on its own predictions on real videos and see whether it's going to work. So we fine-tuned this new CoTracker3 architecture on its own predictions on real data, and it actually worked, which was surprising because the model was training on its own predictions without any additional features or augmentations or anything like that. So we just decided to keep scaling this up, so adding more data, improving some hyperparameters, adding more synthetic trained teachers as well. So teachers trained on Kubrick, and it worked. So the whole thing worked. We had a pipeline to scale synthetic trained point trackers on real data. Here are some results. Circles correspond to synthetic trained models, and triangles correspond to models scaled with this kind of pipeline. So here we scale CoTracker. We show that it improves with more data on all the top feed benchmarks. Here we show the mean of all the top feed benchmarks. Then we also show that local track improves, and the new CoTracker3 architecture, it also improves. And this is our CoTracker3. Here we worked on long occlusions, so we removed the sliding window and decided to process the whole video at once. We also simplified the architecture and removed global matching. And we proposed a pipeline to fine-tune the model on real data, pseudo-labeled by different synthetic trained teacher models. Okay, so that's CoTracker3. And now I'd like to show you this video. And I'm wondering whether you're going to recognize it. Some of you probably will, because it's a famous video on research. And it's actually this video. I think it's surprising that it's still possible to recognize what's going on in the video when we disentangle motion from appearance. And let's take a look at this video again. So I believe that with this kind of models, it's going to be possible to solve dynamic 3D reconstruction. And I think it's a really interesting direction for future research. And yeah, on that note, I'd like to end my presentation. Thank you.